Hi, my name is Shanna Slight. I'm going to do the first SPED talk on data structures. Just a quick review so that we can make sure we're picking the right data structures for the function we need in our project. So first we have arrays and vectors, which you're probably very familiar with. The difference is that arrays have a declared and unchanging size, while vectors can change at runtime. Because arrays have a static size, you can have an array of arrays to model any number of dimensions without too many problems. Vectors, on the other hand, if your vector changes size, and you have a vector of vectors, you have to change the parent and child vectors. So that can introduce a lot of errors. Both have random access. You can access them via their index. But they're not very great at inserting information in between two items. So you have data in slot 0 and slot 1. You can't readily insert data in like a slot 0.5. You can have associative arrays, where instead of an index, you have a key of a different data type. Maps are a specialized associative array where those keys can be different data types from each other. The linked lists, that's what you want to use if you want to be inserting data in between previous data points. In all of these graphics, a gray box means that it is a pointer. So when you initialize a linked list, you get a first pointer, which links to your first piece of data, and then next pointer, next, as it goes on. This graphic is a unidirectional list. You can also have a bidirectional list, where you not only have a next pointer, but also a previous pointer, so you can track the list both ways. Queues are a first in, first out data structure. They're based off of an array, and the queue records where the front of the line and the back of the line is, so you know where to add new data at the back, or where to pop off data from the front. Stack is similar, but it's a last in, first out. And it's also implemented using an array, but it records the capacity and where the top of the stack is. Trees. Okay, so our tree is based off of the linked list. This graphic is a binary tree, so you have a left and a right child linked to new data there. The reason we might use a binary tree versus a linked list or another data type is that there are readily available search functions as long as your tree is balanced. So depending on how that tree is constructed, it could be quite unbalanced and end up being a linked list at worst case scenario. So we have a number of ways to prevent this. An AVL tree is a binary tree that also records a balance factor and then rotates branches to keep that balance factor between 1 and -1. A 2, 3, 4 tree gives you a little more flexibility. Instead of being a binary tree, it supports up to 4 child pointers, and it maintains balance by having all leaves on the same level. Red-black trees are a variation on the 2, 3, 4 trees, which color nodes red or black, and use a series of rules to maintain balance on that tree so that it is readily searchable. So next we have what I'll be using for my project, which is graphs and digraphs. So a digraph is a directional graph. As you can see in the graphic, we have a little simple graph just with 4 nodes, and you can see the data structure to the right of it looks a lot like a linked list or a tree. This graph only has 2 children per parent node, you might say, or 2 links. So one is linked to 2 and 3, but not 4. So we only need 2 spaces for pointers. But not all graphs are going to be like that. For example, plain old graphs, not digraphs, are bidirectional. So like a bidirectional linked list, you're going to need return pointers as well. A complete graph in mathematics is a graph where all nodes are connected to all other nodes. So you're going to need as many pointers as you have nodes. And as you add nodes to the graph, you're going to need to add pointers to each. So C++ does have a digraph class, which is graph.h, you can download. It allows you to add unlimited nodes and edges, So these links, they're called edges in graph theory in math. They're called arcs in computer science. So don't let that get you too wound up. So that can help adding extra nodes. It does not have the bidirectional the way a graph would. You have to do that manually. And it also does not have the ability to attach data to the links or edges or arcs themselves. So you can see in the corner, I've created a little diagram of what a data structure might look like where you have labels or data connected to those links. So that's what I'm doing right now this week. Hopefully this quick review has helped you remember some of your different options more than just arrays and vectors so that you can pick what's best for you. And thank you so much.